Yep. Mhm.
The first question we were asking about the deflection.
Mhm.
Is that like the results we get for the deformation?
Yes, yeah, deflection,
The
deformation,
maximum deformation?
exactly.
Oh, okay.
Mhm.
I was just trying to make sure.
Oh, yeah, yeah.
Yeah.
Mhm.
Sure. A lot different.
The pressure on the side. So I have the static on the biggest. only the, master. Yeah, so. Reading analysis pressure. Back to work. But I think you have to follow the mechanics like we saw. Yeah, okay, got it.
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good to hear. All right, so today's going to be a review day. So I thought, just kind of reading your guys' introduction emails. Just everyone's coming from different backgrounds. Sometimes it's been a while since you've taken classes, so I thought it'd be useful just to kind of go over and review some concepts of mechanics, strength of materials, concepts of stress and strain, just because these are going to be pretty consistent throughout the entire course. So I thought I would spend some time reviewing that today. Before we get back into the FDA stuff on next week. So my plan is to kind of review this today. On Tuesday, we'll start talking about meshing. Next Thursday is going to be our next activity. And then we'll go from there. But I think, getting a review of strength of materials, I think kind of puts a little bit more context in some of the results that we're getting, the deformation, the stress especially, just so that you kind of know what you're looking at and kind of get some context about that. Okay. Okay. So if you just took solid mechanics just yesterday, then this will be hopefully a very quick review. If you haven't seen it in a while, hopefully this is kind of useful for. Any questions I can answer before we get started? Any questions on the activity that's due? Okay, all right, so let's go and get started. So these notes that I have here, the notes that I have are actually even more comprehensive because I use these notes for a lot of classes that I teach. So they actually start from this, what is a force? What is a moment? What is a system of forces? So I think we'll probably skip those things. Hopefully everyone understands the concept of force. But I did want to skip ahead to the review on strength of materials. Right? And so if you're following along with the posted lecture notes, I believe this starts on page 6 of those lecture notes. Okay. So strength of materials. And so strength of materials refers to basically the study of the mechanics of materials and how they deform in response to external loading. So just intuitively, if you have some kind of structure, you apply some forces to it, you expect the structure to respond. Unless you're a little wimpy person like me that can't push things around. Generally when you apply force to a material, you expect it to deform slightly. You expect some stresses to develop on the inside. And if you're strong enough, you could even break the material. And so we'll go through material failure a little bit today too. Okay. But first, let's go over the concept of stress. Okay, so when I talk about stress, we're talking about mechanical stress within a material Or in other words, these refer to the internal forces that develop within that material. Okay. And so what happens when you take a material and you apply some loads to it, in order to keep that structure, in order to keep that material in static equilibrium with itself, internal forces have to develop in order to keep that equilibrium. And we call those internal forces stresses. Okay. All right. So even though I say that stress here are internal forces, the units for stress is not actually newtons. So actually the units that we typically use for stress is actually force divided by area. And so if you want to put this in SI units, like we typically do, this is newtons per meter square. Okay. And Newton per meter square is actually a special unit in SI. So you'll often hear this called pascals, or any of the derivative quantities from Pascal. So kilopascal, megapascal, gigapascal. Those are probably you'll hear more often. But a Pascal is nothing more than a Newton per square meter. Okay. The English unit equivalent or the imperial unit equivalent is the most standard one, I think, is pounds per square inch. Or probably what you hear more often, PSI. PSI stands for pounds per square inch. Notice how the units for stress is the same as pressure. And you know, both of those describe a force distributed over an area. Just the way that we interpret stress is a little bit different than the way we interpret pressure. So it's a little bit confusing because they have the same units, but they have slightly different connotations and slightly different applications. But just know that stress and pressure have the same units. Okay. Okay. So, you know, don't get confused by that. And it's even more confusing later on. We'll go over the common material product called the Young's modulus, which also has the same units as stress. And so, you know, this unit here, if you work in structural mechanics, strength of materials, you'll see these units quite often. Okay, so let's talk about why these develop. So let me just do a very simple example just to illustrate to you. Okay. So let's look at a rod that's in tension. Okay. All right, so we're going to look at a structural rod like this. Okay. It's going to be in tension, so we're going to be applying a tensile force on both sides. Okay. All right, so we're literally taking this rod and trying to pull it apart like this. Okay. In order for the rod to be in static equilibrium, the sum of the forces must be zero. So the magnitude of the tensile force on both sides is going to be T. Okay, they're just in opposite directions. So as a whole, you know, we can look at this object as a rigid body and say that, yes, this rod is in static equilibrium. If we sum up all the forces on this rod, they equal zero. And so if the sum of the force is equal to 0, there's no acceleration. And if there's no acceleration, that means there's no motion. Okay, assuming there's no initial velocity, which we're assuming. Okay. But if we were to slice this rod, and if we were to kind of look at what's happening internally within the rod, every single part of this rod has to be in static equilibrium as well. Okay? And so, for instance, let's say we took a subsystem. So let's take an imaginary slice down this rod, okay, right down the middle. Okay. And let's look at the subsystem that's just to the right of that cut line. Okay, so let me draw the cut line again. And let's look at this section of the rod just like that. Okay. So since we're just looking at the right side of the rod, we have to include the tensile force on the right. Okay. Right. But since we cut the rod in the middle, we're in our little subsystem here, we're missing the tensile force on the left, right? But since we know that this part of the rod here has to still be in static equilibrium, right? Just because we slice it in the middle doesn't mean that, this part could just now go flying. And so to oppose this tensile force, we recognize the fact that we cut the interior of this rod itself. And so within that rod lies the ability to develop internal forces or internal stresses. Okay. And so what we have here on this cut surface, those purple arrows there are going to be internal forces or stresses that are going to oppose that external force T. And the way that we usually define these forces is that we describe these forces as a force distributed over the cross section of that rod. In other words, in order for this to be in static equilibrium, if we take sigma, where sigma here represents the internal stresses within the rod, okay, and we multiply it by the cross-sectional area, so the area of that slice that we just made, okay? In order for this to be in static equilibrium, this has to be equal in magnitude to the tensile force that's being applied. And then to solve for our value of sigma here, we're just going to divide both sides by A. And so we get sigma, or stress, is equal to force divided by area. Okay. So that, of course, is a very simple case. So that's a very simple case where we have, the force going in a single direction. The internal stresses are all going in the same direction. And so we can compute kind of a very simple formula for stress just like this, okay? In reality, stress is actually a very complex, quantity, which can vary in direction and vary in type as well. Okay. And that's due to the fact that, the loading conditions on a typical material, on a typical part, as well as the geometry on the part are typically very, very complex or complicated. All right, and so, we're probably gonna spend the next 30 minutes talking more about stress and how, how we can actually describe it. All right, any questions on just the concept of stress here? Okay, cool. All right, so next thing I want to discuss is the difference between normal stresses and shear stresses. The first one we have is normal stress. Okay. So normal stresses, normally when you see them drawn, they're usually perpendicular to the surface that they're acting. And so the example that we just did with the rod and tension, those are all normal stresses. So those are perpendicular to the cut point. Okay. Normal stresses have the effect of either pulling the material apart, and so they're going to be separated in tension, or they're going to be compressed directly together in compression. So let me just kind of give you a couple drawings here. Right, so something like this would be a tensile normal stress. Whereas a stress that's going to be pushing inwards, like this would be a compressive normal stress. Okay. So yeah, normally when you talk about normal stresses, it's, people just say it's perpendicular to the surface. But the reason it's perpendicular is because it's either acting to pull it apart or push it together. Well, I guess I shouldn't say, but in a lot of engineering applications, normal stresses are kind of what you're looking at first, unless it's something that has a lot of shearing stresses. Okay. Okay. And so the other type of stress that we usually worry about are what are called shearing stresses or shear stresses. And so shearing stresses in opposite to normal stresses, they act parallel to whatever surface that you're considering. All right, and shearing stresses, the main thing that they're going to be doing is that they're going to cause the material to go through what's called shearing deformation. I know, very, very descriptive, but I'll draw you a picture in a second. I think kind of the easiest way to illustrate shearing stresses and shear deformation is that these are the kinds of stresses that cause the material to slide past each other. That's in kind of the extreme case where you actually get, actual shearing within your material. Okay. Okay. And so visually it looks something like this. And so if you have a surface that's exposed to shearing stresses, the stresses are acting parallel to the surface. Okay. But if you were to kind of visualize it, so let's say that you have a material that's exposed to shear, right? So then kind of the easiest way to illustrate this is through a rod. Okay. Right. So the easiest way to cause shear is to kind of take kind of one of your thumbs and kind of push downwards on one side. Then on the exact same plane, or maybe kind of slightly offset from this, you're going to push up on the other side. Okay. And so in the worst case, that's going to cause a break just like this. Okay. It's going to cause the material to kind of slide past each other. So this is what we call kind of shearing stress or shearing deformation. One reason we usually make the distinction between normal stresses and shear stresses is that a lot of materials have different strengths in one direction or the other. So you may have a material that's very good in resisting normal stresses, and so you can compress it, you can put it in tension, and it's going to be very strong. It's not going to break. But the material may be very weak in shear, and so if you try to shear the material, you might find that you can apply shearing or cause shear deformation with much less force. Okay. So knowing the difference between shearing, normal stresses, shear stresses, and what are the particular strengths of your material is usually something that's important. Okay. Any questions on this? Any questions on normal and shearing stresses? Okay, good. All right, so that's kind of just the general overview of the different types of stresses. But stress also can occur in different directions too, just like we mentioned above, right? But when you combine this fact that stress can occur in different directions and there's different kinds of stresses, right? The state of stress within a material is actually quite complicated. So let's talk about that for a second. All right, and this is usually the terminology that you'll see kind of expressed in the literature and technical manuals and stuff like that. Is what is the state of stress? Okay. Okay. And so if we kind of make the assumption that we're considering, both normal stresses and shear stresses, and we make the assumption that we're working in three-dimensional space, one way that you can think of it is that each type of stress is going to have components in each of the three cardinal directions. Okay. So in every material, there is an X component of the normal stress, a Y component of the normal stress, a Z component of the normal stress, and there are three components of the shear stress as well. The way that we define the shear stress is actually a little bit complicated because it depends on the plane. We'll get to that in a second. But if we just do a little bit of arithmetic here, so if we take three components of normal stress, three components of shear stress, that means at any given point within a material, there are actually 6 total independent components of stress. Okay. I forgot a word. So it's 6 distinct components of stress. Okay. There's actually more. There's actually 9 components of stress. Because unlike, I think probably everyone's used to the concept of vector quantity. And so when you're describing, deformation, there's an X, Y, Z component of deformation. That's 3 components. It's a vector quantity. Stress takes it a level above that. So stress is what we call a tensor quantity. So its definition is actually defined by a matrix, not by a vector, which makes things very, very complex, and I think very intimidating for most people to know. Okay. So even though at every point in a material we have a stress matrix, 3x3 stress matrix, which if you do the math, there's 9 components in a 3x3 matrix. Only 6 of these are actually unique, because there are some repeated entries in them. Okay. Okay, so let's go through the 6 components of stress. And so on the one hand, we have sigma xx. And so this is what we call the normal stress in the x direction. We have sigma yy. This is normal stress in the y direction. Sigma zz, which is normal stress in the z direction. So those are pretty straightforward. So the normal stresses have 3 standard components, 1 in each cardinal direction. Okay. With the shear stresses, it gets a little bit more complicated. Okay. So first we have tau xy. Okay. And another way that we call this, or its symmetry, its symmetric component is tau yx. So this is a shear stress. This is a shear stress in the y direction that's parallel to an x facing face. I know that sounds really confusing, but I'll kind of illustrate for that. I'll illustrate it for you once I kind of finish listing all the components. Okay, and that is actually equivalent to the shear stress that's in the x direction that's on a y direction facing. Okay. The fifth component is also a shear stress. So we have tau xz, which is the same as tau zx. So this is a shear stress. And in the z direction. I just realized on the definition above, I forgot to say, in the definition above, it should be shear stress in the y direction. I forgot the y there. Okay. So coming back to number 5 here. So tau xz is a shear stress in the z direction. And so this is on a face that faces the x direction. And then the final component of stress is tau yz, which its symmetric component is tau zx. And so this right here is a shear stress in the z direction. And this is on a face that faces the y direction. Question, yes. There is a tau zy, yes. Oh, thank you. That is a typo. So the tau zy should be the opposite component for this one. Yeah, thank you for catching that. I know this sounds like word salad, but let me go ahead and draw it. So typically the way that these stress states are visualized is by drawing a cube. Okay. And so if you have a typical material here, okay, so I'm going to draw an amorphous potato, just like I did before. Okay. At any given point, we can illustrate the stress state by drawing a little cube, okay, or at least visualizing a cube in that location. Okay. Let me go ahead and expand this cube. Let me draw the Cartesian axis as well, just so you know kind of what my conventions are. And so typically, when I draw things, I draw the x direction going to the right, z direction is going upwards, and then y direction is coming out towards the page. Okay. Okay. So let's start with the normal stresses, because those are kind of easiest to visualize. Let me use purple for the normal stresses. Okay. So normal stresses, remember, act perpendicular to the face, and they act to kind of either pull this apart or compress it together. Okay. So we have 3 components, and so I'm going to go ahead and draw them on the 3 sides of the cube here that we can see. Okay. And so we have sigma xx that's acting perpendicular to that face faces the x direction. So that is normal force in the x direction. We have sigma zz, which is going perpendicular upwards. It's perpendicular to that faces the z direction. And then we have sigma yy that's pointing in the y direction that is, perpendicular to that face facing the y direction. Okay. Oh, and this cube here, we assume it's in static equilibrium. So there is an equal and opposite force on both sides. So on the other side, it's a little bit hard to draw because it's kind of obscured. but there is another sigma XX on this side here, okay? That's on the face that's opposite to the other one. And on the bottom here, there's also sigma ZZ, okay? Just because, there's no, we assume that this cube here is in static equilibrium. And of course, there's one coming out the back too, and so there's sigma YY too. Okay. So that's the normal stresses. So normal stresses are usually pretty easy to visualize. So you draw your cube, you draw just strong lines that are perpendicular to every face, and those are going to be your normal stresses. Okay. The shear stresses get a little bit complicated because in each given face, you can have shear stresses in two directions. Okay. Let me use the X face first, just to kind of illustrate to you. Okay? So let me use this face here, just to kind of show you. Okay. And so on that face right there, we can have a shear stress that's going in the Z direction. Okay. So that here is tau X, tau XZ. Okay. And we can have a shear stress that goes in the Y direction that's parallel to that face. And so we also have a shear stress in this direction, and that's going to be tau XY. So for the shear stresses, it gets a little bit complicated because they have to be parallel to a surface. Each surface can have two components that are parallel to that surface. Okay. So that's why there's so many components of the shear stress, and it gets a little bit confusing, explaining it as well. But hopefully this makes it a bit more clear. And there's shear stresses. There's two components of shear stress on every other face. Okay, so I'll draw a few more. And so, for instance, we have this direction here. So this is tau YZ. We have this direction here, which is tau YX. Okay. And then on the top surface here, we have tau ZY. And right here, we have tau ZX. Okay. And then there's corresponding matching shear forces on the three faces that you can't see. So on the back side as well. Okay. Any questions on this figure here? Okay, good. All right, so when you're using ANSYS, and you can definitely try this out in the activity next week, you can actually ask ANSYS to show you the different components of the stress. So typically, what we display is what's called the equivalent stress. I'll define that in a second. But you can actually ask ANSYS to show you, the normal stresses as well as the shear stresses, and then you can show the different components of the normal stress and the shear stresses as well. Okay. Okay, good. But so all of these definitions of stress are great. But that's not the one that we saw last week, right? So when you guys did your activity one, I asked you to show me a very particular component of the stress, or a particular type of stress called the equivalent stress. Sometimes it's called the von Mises stress. Okay? So let's go over that concept. Right. Okay, so what is the equivalent stress, or what do we mean by it? So, one thing that, maybe is a thought that's crossing your mind right now, that stress is very complicated, right? It's already complicated to think about a vector quantity, but to think of a tensor quantity is even more difficult to kind of visualize. Just to think that at any given point within a material, there's not only three directions of stress, but there are different types of stress, and they can all have their own directions. And so, you guys aren't alone in thinking that, unless you're an engineering savant and you're thinking, stress isn't hard. For most people, thinking about stress is pretty hard. So, when you're doing finite elements and you're viewing the results, the way that we typically view finite element results is that we view them in a color contour plot, right? The thing is with color contour plots, it's really hard to kind of illustrate the fact that different quantities can have different components. And so the equivalent stress is kind of a way to kind of take a very complicated quantity like stress and visualize it as a scalar quantity instead of a tensor quantity. Okay. So our mind kind of already does this with vector quantities, right? And so think about the total deformation plot that you guys all produced in activity one, right? Total deformation is a little bit easier to, I think, to visualize just because, you guys, mostly everyone learns about vector quantities when they're going through kind of their education, right? And so one thing that you can do with the vector is you can find the magnitude of the vector or the length of the vector, right? So deformation is a vector quantity, and so it has components in x, y, and z directions. Okay. And so at any given point, there are three components to the deformation. There's the x component, the y component, and the z component, right? And so if you want, you can ask ANSYS to show you the individual components of deformation. And so you can see, which parts of my model are deforming in the x direction, which are deforming in the y direction, how much of the deformation in the z direction, okay? But a lot of times, especially when you're first looking at your FEA results, you want to find out, how much of the total deformation is there, or what's the magnitude of deformation, right? So the magnitude of a vector like this is we simply use our magnitude formula here. Okay. So this is deformation magnitude. Okay. This is simply dx squared plus dy squared plus dz squared. Okay. Right. So that's the way that you take the magnitude of the vector. Okay. And this is the quantity that's actually displayed to you in ANSYS. So it doesn't tell you, each individual component of deformation, but it tells you how much of the deformation is there. So you're basically taking a vector quantity, you're applying a formula, and you're transforming the components into a scalar quantity that's easy to visualize. Okay. With that, that concept of taking a vector and finding its magnitude, I think is more or less, I think, at least easy to kind of visualize. For stress, it's not that easy because you don't have, stress is not a vector quantity, it is a tensor quantity. And so as such, we need to have a new formula or a different formula to compute what we call the equivalent stress or the stress magnitude. And I always forget the formula. So actually, let me look it up. And I don't have it in my notes, actually. On Mises stress. Wikipedia. Here it is. Okay. Okay, so the von Mises stress, not that you would ever need this formula, at least not in this class, but it's good to know just in general. Okay. So the von Mises stress is sigma v is equal to square root. So you can see it does share some quantities with the vector magnitude. So we do have a square root in here. Okay. And this is multiplied by 1/2 sigma xx minus sigma yy quantity squared plus 1/2 sigma xx minus sigma zz quantity squared plus 1/2 sigma yy minus sigma zz quantity squared. Okay, so that's all the normal components of the stress. Okay. Plus, so this is still under the square root. Actually, let me just zoom out and just add it here just to make it a bit more clear. Okay. Now we have all the shear stress components. And remember, even though, we can swap the indices for the shear stress, but, there's only 3 distinct components of the shear stress. And so you can kind of, interchange those. Okay. And so we have 3 multiplied by tau xy squared plus tau xz squared plus tau yz squared. Okay. Again, I'm not going to test you on this formula. We're not going to be plugging things into this formula. This is kind of just for your interest. If you're curious about how the equivalent stress is okay. So the exact formula for this is again, not too important. It's more about how we interpret it, right? And so the way that we interpret equivalent stress and the way that you're going to see it in all of your activities and the projects is you can think of that as kind of like the stress magnitude. All right. Any questions on equivalent stress? Okay, good. All right. In activity 2, actually, we're going to use the equivalent stress for one other application, and this is a very common application for the equivalent stress. And so one question that is usually asked whenever you're running a finite element analysis is you're curious to see whether or not your material or whether or not your part is going to fail or whether or not it's going to prove. And so if you have a part, you expose it to loads and constraints. You're oftentimes curious to see, is this part going to fail? Is this part going to break, or so on and so forth, okay? So the common way to do this, or I would say kind of the quick and dirty way to do this, is to use FEA to compute the equivalent stress, and then to compare the equivalent stress to something called the yield strength in the material. Okay? So every material has something called the yield strength, which basically describes the maximum amount of internal stress that it can withstand before it starts to break in space. Okay. So one kind of quick way to see, if your part is going to fail or not after an FEA is to apply your loads, apply your constraints, run the simulation, compute the equivalent stress, and then compare the maximum value of equivalent stress to the yield strength of that material. If the equivalent stress is greater than the yield strength, then it's going to break. If not, then your part is going to be fine. Okay? So in other words, you're going to check. Okay? Check the maximum von Mises stress. Okay? If that's greater than or equal to the yield strength, and so yield strength, we usually give it the symbol sigma y. Okay? This right here is the maximum equivalent stress. This right here is the yield strength. And so if that's true, then your part is going to break. So if you're designing your part and you basically bring the yield strength, you basically bring the equivalent stress right up to the yield strength. That's a little bit risky. So unless you're working on airplanes, you don't want to be in that regime where you're designing something that's going to be right before it breaks. That's usually not a comfortable place to be. So usually what's done in design is to apply something called a factor of safety. Okay. Because when you're doing FEA, things aren't usually quite exact, and so the true stress may be a little bit higher than what you're estimating, and so you want to factor in some wiggle room. You want to factor in some factor of safety, just so that you can sleep a little bit better. Okay. So the way to apply factor of safety in kind of a very simple way is so factor of safety is usually some kind of number, and so it's usually some number greater than 1. Okay. Okay. And the kind of the simplest way to use it is to use that to scale down the yield strength, or the highest tolerable yield strength. And so, the criteria above, so let's call factor of safety, let's call it F. Okay. Okay. And so if F is your factor of safety, then the above criteria would then be modified. Okay. And so in order to characterize material failure with accounting for a factor of safety, you would then do sigma V max. If that's greater than or equal to sigma Y divided by F, okay, right? And so F is some number greater than 1, then the effective yield strength or the maximum threshold for the yield strength will then be reduced, okay? And so for a simple case, let's say we have a factor of safety of 2, okay? And so if you have a factor of safety of 2, then the maximum stress that you can tolerate is half of the yield strength, okay? That's usually pretty safe. Well, it depends on what you're designing. If you're designing an airplane, then factor of safety 2 is great. If you're designing a bridge, then factor of safety 2 may probably not be enough. So, it kind of depends on your application. Okay. But what the factor of safety does is that it effectively lowers your strength. Okay. Okay. So this is something that you'll see in activity 2. So in activity 2, I'll give you guys a little bit of a preview. You're going to be designing a bike crane, or you're going to be running analysis on a bike crane. And you want to basically determine if that bike crank is going to fail with a factor of safety. All right, any questions on this? Okay. All right, so last thing I want to go over today. Let's go over the relationship between stress and strain in a material. Okay, so we spent the majority of today talking about stress, right? And stress is one of the most important quantities in a structural FEA. Within any given material, stress is very closely related to another quantity called strain. Okay? So let's define strain really quickly. So strain is a unitless quantity, which is quite fascinating. So strain is a unitless quantity that represents the relative amount of deformation that a structure will undergo when it's exposed to load. Okay? The key word here is relative, right? And that's the reason why it's unitless. Okay. And so if strain occurs, then why are we measuring the deformation? Or what's the difference between total deformation and strain? Okay. Well, strain is a relative quantity. So I think kind of the easiest way to visualize strain is basically it's a measure of how much a certain point deforms relative to its resting configuration. So I think the easiest way to visualize strain, and I think the way that most people kind of learn about strain, is through a simple one-dimensional rod. Okay. Okay. So if you have a rod that's attached to a wall like this, and so let's say that we apply a tensile force, okay, T. If you apply enough force, or even for a very small amount of force, the rod is going to stretch, right? And so let's say the original length of the rod is L. And then after you apply the force, the rod is going to stretch out to some amount like this. Okay? And so the amount that the rod elongates will be given by delta L. Okay? The strain in this rod is nothing more than just the change in length, delta L, divided by the original length, L. Okay? So that's how strain is defined in kind of a one-dimensional context. Now in two dimensions, three dimensions, the definition becomes a lot more complex. In fact, strain has all of the same components as stress. And so there are normal strains and shear strains as well. There's also equivalent strain that you can view in analysis too. Okay. But that's generally the idea. So strain measures, relative to its original configuration, how much has this part deformed. Okay. The quantity total deformation that you're viewing is very similar to this, except total deformation does not have L in the denominator. Okay? So total deformation just says, what is the ruler definition? So, you take your part, you apply and load. What is, the ruler distance between where this point was and where it is? That's total deformation. Strain will take this and we'll scale it by the original size or the original length of it. So typically, when I have you guys, do the ANSYS activities, do the project, I have you guys report total deformation, because that usually is a little bit easier to visualize, a little bit easier to interpret than, looking at strain. Okay. Okay. So that's strain in a nutshell. So it turns out, for most materials, stress and strain are actually very closely related to each other. And so in a material that we call linear, and so in a linear material, a linear isotropic material, stress and strain are actually linearly related to each other. Okay? And in fact, they're related according to a formula that you've probably seen, a lot in your previous, strength of materials classes, which is Hooke's law. Okay? So Hooke's law basically says that the stress in a linear isotropic material is equal to the Young's modulus multiplied by the strain. Okay. For sigma here, this is the stress. Epsilon here, that's the strain. And E here is the Young's modulus. Okay. You remember from activity 1, there was a part where we confirmed that the Young's modulus for the material is such. Okay. This is where it factors in. And so for such kind of a simple equation like this, we can actually graph it. And so this is probably kind of what you've seen before in the past too. Okay. So for a typical stress strain curve for a linear material, it's just a straight line. Right. So in typical stress strain curve, strain is on the horizontal axis, stress on the vertical axis. Okay. And what we have is just a line. Okay. Where the slope of this line, the slope of the line is the Young's modulus. All right, so this is, oh, question, yes. Yeah, isotropic basically means that it has the same strength in every direction. So it doesn't matter if you load it, you know, in the X direction, Y direction, Z direction, you're going to experience the same strength. Yeah, we'll go over that a lot more when we go over material properties. But for most metals, and we're going to be dealing with metals a lot in this class, those are all isotropic. Yeah, good question. So, you know, the fact that stress and strain are linearly related to each other, you know, this is part of the reason why I don't have you guys display strain. So because to get strain, all you have to do is just take stress and just divide by the Young's modulus. So it's usually not too exciting from that perspective. Okay. So this linear relationship, you know, is something that's very commonly taught in strength of materials, but it's actually only valid up to a certain point. This is not true, indefinitely. You can't just keep applying force to a material and then it's just going to deform linearly according to that, right? Even just intuitively, you expect that if you apply increasing stress to a material, it's going to break eventually, right? We just finished talking about failure, right? And so usually this linear relationship is only valid for relatively small deformations within the material. And of course, the operative keyword here is relatively small. So what is relatively small mean? So generally, I would say, a relatively small deformation is one that is less than 10% of the total length or the total size of your mark. Okay. Once you kind of get beyond that 10% mark, then you start to get into what's called large deformation. Okay. So once you get past this point, once you get past that threshold of relatively small deformations, the nature of the stress-strain relationship actually changes within the material. And so that's the part where you start to get what's called plastic deformation. And so plastic deformation, if you kind of continue on with the stress-strain curve, you're going to see that the curve is no longer linear. And so it starts to kind of follow almost like a square root type of relationship. Okay. And so, for every linear material, there is kind of a region that's close to the origin called the linear region. And then after a certain point, this curve starts to kind of take off and it starts to kind of follow kind of a curved region like that. Okay? Eventually, you're going to reach a point where you're going to reach the yield strength of the material. Okay. And so if you keep applying increasing stress or increasing load to a material, you're going to see the material go through kind of three regimes here. So in the first regime, you have kind of linear, we call linear small deformation. Okay. The next section is plastic deformation. And then once you're going to reach the yield strength, then you just have material failure. Okay. That's not how all materials behave. Material science is actually quite complicated. And we're going to talk about kind of more complex material models in this class. But for a very simple linear isotropic material, you know, like most metals are, this is the type of behavior that you can expect, okay? Now, an interesting thing about ANSYS is that, you know, modeling plastic deformation or simulating it is actually quite expensive. It's quite complicated because that's when nonlinearities kind of creep into play. So ANSYS, at least the one that we're using, actually assumes linear deformation all the way through. And so in its default state, ANSYS actually doesn't have any way to know if your material is going to be plastic deformation or even failure. And so you can actually try this with your activity too. So, you know, apply a load that's maybe 100 times greater than what you had, and you're going to see that the part is going to deform by 100 times too, even if it doesn't make any sense. You may have a part that's only, you know, 10 inches long, but, you know, you keep applying increasing loads, you may have a deformation of, you know, 100 inches, which makes no sense at all. So, you know, one thing to kind of keep in mind when you're using, so you want to kind of be careful. All right, any questions on this? Okay, last thing I want to mention today, just because, you know, we're going to see it in the activity next week as well. Let's talk about the Poisson's ratio. So we just finished talking about the Young's modulus. So the Young's modulus is probably the main material property that you're familiar with. Young's modulus determines the slope of the stress strain curve, and generally materials with a higher Young's modulus have higher strength. Okay. But another material property that we're going to be seeing is the Poisson's ratio. Okay? And so Poisson's ratio is a number, and so just like strain, it doesn't have any units. The way to interpret Poisson's ratio is a little bit, you know, not as clear. And even the definition that I have right now, you know, is not, you know, I would say doesn't cover it 100%. Okay. But the way that I think of Poisson's ratio is that it measures how much a material will deform in directions perpendicular to the load. Okay. So what do I mean by that? So, you know, again, let me use a very simple case here to kind of illustrate. Okay. So let's say that we have a rectangle. Okay. I guess you can call it a rod too, right? So back where we started. So let's apply a tensile force on both sides. So tension on this side, tension on this side. Okay. Right. So if the tension is high enough, and so what we generally expect in this situation is that this rod should elongate, right? And so you should get some elongation on this side. You should get some elongation on this side, right? So the total length of that rod should increase by applying this tensile, okay? That makes sense. That's consistent with everything that we've discussed. You apply a load that applies stress. That stress causes strain, and that strain kind of reflects how much the part is deformed. Okay. One factor that we didn't account for is the fact that, you know, this rod has a fixed amount of mass associated, right? And so, you know, if you're increasing the length of the rod, you know, that increased length is not coming from the void. It's not coming from nothing. And so that increased length has to come from somewhere, right? And so where that length comes from is the fact that, you know, other parts of the rod are actually getting thinner. Okay. Now I've exaggerated it here, so, you know, usually it's not to this extreme, unless you're pulling a lot, right? But the Poisson's ratio, what that measures is the characteristic, or it determines the behavior of how, you know, material kind of shifts around and you have deformation that is kind of different in a different direction than the loading itself. Okay. And so in this particular situation where you have kind of a material that's getting thinner as it's elongating, that's a phenomenon known as necking. Right? And so you have a neck that kind of forms in your material. So the Poisson's ratio kind of determines that. Okay? That's not the only thing Poisson's ratio does. Poisson's ratio is a lot more, of course, in 3D situations, it's more complicated than this. But I think that's the easiest, kind of simplest example I can give to what the Poisson's ratio does. Okay? And Poisson's ratio typically has a value of 0.0 to 0.5. Okay? So you're not going to see Poisson's ratio is different than that. And that's mostly just how it's defined and how it's used in equations. All right, any questions on anything we discussed today? Yeah. Yes. I wrote everything except the symbol. So yeah, Poisson's ratio is a nu, so it's kind of like a V. Yeah, thank you for that. Any other questions on this stuff? Okay, all right, so that's all we have time for this week. So when we come back on Tuesday, we're gonna open up with meshing. So that'll be kind of exciting. And then next Thursday, we'll do our activities. So thank you guys for coming this week. I hope you guys have a good weekend, and I will see you guys on Tuesday. Dominic, did you hear from the department about?
Yeah, I got the.
Oh, perfect, okay.
I already joined.
Okay, perfect,
Yeah.
perfect. Yeah, Dr. Martin, he doesn't tell me when he does these things anymore, he just
It
does it.
happened- They happen like 8 in the morning or 9.
Oh, really? Okay, wow, that's really
The
fast.
next day,
Okay,
so like,
okay, yeah, he didn't tell me, so yeah, but he's kind of sick, so I think he's just,
oh,
okay, good. I just want to make sure you're.
and I'll send pictures of this all.
Okay. Okay. We're good. See you guys.